Welcome to Agentic AI World, interview prep for senior engineers. I'm your host, and today we're diving into episode 91, AI State Space Models Deep Dive, how senior engineers master efficient sequence modeling in modern AI systems. If you've been following the series, we've covered transformers, attention, RNNs, and diffusion models. Today we tackle state space models, the architecture that's challenging transformers for long sequence dominance. This is interview gold for 2026. Let's start with the core question. Why do we even need state space models? Transformers are incredible, but they have a fundamental scaling problem with sequence length. Attention is quadratic in sequence length. Double your context, quadruple your compute. For a 100K token document, this becomes financially and computationally brutal. RNNs are linear, but they can't parallelize during training. State space models, SSMs, aim for the best of both worlds, linear complexity and parallel training. The key insight of SSMs is that they model sequences as continuous time dynamical systems. The state at any time step is a compressed summary of all history, updated by a simple linear recurrence. During training, you can unfold this into a convolution, which parallelizes beautifully on GPUs. During inference, you run it as a recurrence. O of 1 memory per step, no growing KV cache. Let's talk about the breakthrough model, Mamba. Mamba, released by Albert Gu and Tri Dao in late 2023, is the SSM that made the industry take notice. Its key innovation is the selective state space mechanism. Classical SSMs had fixed transition matrices. They treated all tokens equally. Mamba makes the state transition parameters input-dependent. The model learns to selectively remember or forget based on the content of each token. This is analogous to attention's content-based routing, but computed without the quadratic bottleneck. Mamba's hardware-aware algorithm is equally important. It avoids materializing the full state in HBM memory by fusing operations in CUDA kernels. This makes it 5x faster than transformers at equivalent sequence lengths in practice, not just in theory. Now let's get into what a senior engineer actually needs to know for interviews. First, the mathematical foundation. An SSM is defined by four matrices: A, B, C, and D. A is the state transition matrix, how the hidden state evolves. B is the input projection. C is the output projection. D is the direct feed-through. The continuous time equations are hidden state derivative equals A times hidden state plus B times input. Output equals C times hidden state plus D times input. For discrete sequences, you discretize using zero-order hold or bilinear methods, which gives you effective matrices A bar and B bar. This is what you actually implement in code. Second, HiPPO theory. This is the theoretical backbone explaining why SSMs work. HiPPO, high-order polynomial projection operators, gives you principled ways to initialize the A matrix so that the state optimally compresses the history of the input signal. The key matrices are HiPPO for Legendre measure, roughly uniform history weighting, and HiPPO for Laguerre measure, exponentially decaying history. S4, the predecessor to Mamba, used HiPPO as its a matrix initialization. This is what interviewers love asking about. Can you explain why SSMs work theoretically, not just how to use them? Third, the training-inference duality. This is crucial for system design interviews. During training with teacher forcing, you compute the SSM as a causal convolution using FFT. This is O of L log L and parallelizes across sequence length. During autoregressive inference, you use the recurrent form, O of 1 memory, O of 1 per step computation. This is a dramatic improvement over transformers whose KV cache grows O of L during inference. For a 1 million token context, a Mamba-style model needs kilobytes of state versus gigabytes for a transformer KV cache. Fourth, architectural integration. In practice, SSMs are rarely used alone. Mamba blocks alternate with MLP layers similar to transformer blocks. The Mamba2 paper introduced the SSD, structured state space duality, framework, showing that attention and SSMs are actually special cases of a more general matrix multiplication framework. This allows hybrid architectures like Jamba, which alternates transformer and Mamba layers, getting the best of both worlds. SSMs for long-range efficiency. attention for precise token interactions. Now let's do a mock interview question. You're designing a document processing system that needs to handle legal contracts up to 500 pages, roughly 250,000 tokens, with near real-time response. The current transformer-based system is too slow and too expensive. How do you re-architect it using SSMs? Here's how a senior engineer answers this. First, evaluate the workload. Legal contract processing needs precise entity extraction, clause-level reasoning, and cross-reference detection. This maps to both long-range dependencies. SSMs excel here, and precise local attention, where transformers are stronger. Second, choose a hybrid architecture. Pure Mamba may miss fine-grained interactions in dense legal language. Use a Jamba-style hybrid. Mamba layers for the bulk of sequence compression, sparse transformer attention layers every 4 to 8 blocks for precise interactions. This cuts memory from O of L squared to roughly O of L while preserving accuracy. Third, handle the throughput challenge. Legal documents arrive in batches. SSMs are cache-friendly. During inference, the recurrent state is fixed size regardless of document length. You can process 10 documents simultaneously with the same memory as one transformer processing one document. This is a 10x throughput improvement. Fourth, quantization strategy. SSM state matrices are small and sensitivity to quantization is lower than attention weights. You can int8 quantize the state transition parameters while keeping projection matrices in BF16. This reduces the already small memory footprint further. Fifth, evaluation. SSMs can underperform on tasks requiring exact token retrieval, the needle in a haystack problem. Benchmark specifically on retrieval-heavy contract clauses before shipping to production. A follow-up question interviewers love. How do SSMs handle positional information? Great answer. SSMs implicitly encode position through the recurrence. Earlier tokens propagate through more state transitions than later tokens, naturally encoding temporal position. There's no explicit positional embedding needed. However, this means SSMs are inherently causal. They see only the past. For bidirectional tasks like classification, you run 2 SSMs in parallel, one forward, one backward, and concatenate their states. This is the BiMamba architecture. Let's talk about the competitive landscape, because interviewers ask about trade-offs. State space models versus transformers. SSMs win on long sequences, memory efficiency, and inference throughput. Transformers win on in-context learning for short sequences, precise retrieval tasks, and mature tooling. The current frontier is hybrid architectures that combine both.